Welcome to this topic of the Demystifying IPv6 course on IPv6 addressing. This topic is actually the second part of a two-part series on the IPv6 addressing. The Internet Assigned Numbers Authority, or IANA, is responsible for the global coordination of the DNS route, IP addressing, and other Internet Protocol resources. Specifically, the IANA allocates and maintains unique codes and numbering systems that are used in the technical standards or protocols that drive the Internet. IANA's various activities can be broadly grouped into three categories: assigning domain names, protocol assignments, and number resources. For the number resources specifically, the IANA coordinates the global pool of IP and AS, or autonomous system numbers, providing them to regional Internet registries, or RIRs. Both IPv4 and IPv6 addresses are generally assigned in a hierarchical manner. Users are assigned IP addresses by Internet Service Providers, or ISPs, and ISPs obtain allocations of IP addresses from local Internet registries, or national Internet registries, or from their appropriate regional Internet registry. The AFRINIC, or African Network Information Center, covers the African region. The APNIC, or Asia Pacific Network Information Center, covers the Asia Pacific region. ARIN, or the American Registry for Internet Numbers, covers the North American region. LACNIC, or the Latin America and Caribbean Network Information Center, covers Latin America and some Caribbean islands. And finally, RIPE NCC, or the Réseau IP Européens, or French for European IP Networks, covers Europe and the Middle East and Central Asia. This slide depicts the IPv4 exhaustion counter as of March 26, 2011. At the bottom of the screen, you can see that there is a link that you can access to view this exhaustion counter yourself. One thing you'll notice is as of February 3, 2011, the IANA has exhausted all the available blocks. In other words, it's allocated everything it has to the regional information registries. And as you can see, the regional information registries are depleting their resources as well. So the IPv6 address space is 128 binary bits. And as you can see, there is a block called the Global Unicast block, which starts with 001, which in fact is 1/8 of the total address block available, is what we're currently using to allocate global unique IPv6 addresses today, as per RFC 3587. There are a few other blocks, smaller portions of the address space, which have been allocated for things like unique local addresses, link local, and the multicast address space. Obviously, there are many blocks, many available IPv6 addresses that are not even being currently allocated today, and who knows if and when they ever will be. So, some of the special addresses that I'll talk about here, starting with the link local address space. And as you can see, I've depicted it in a number of ways at the top of the screen. It's out of the block that starts with FE80::/10. Or you can say the link local unicast address starts with an FE80::/64 prefix. In other words, the remaining 48 bits are all zeros. And you could also say the prefix FE80::/ is followed by the device's interface ID. So the idea with link local is to scope the packets that are sent to or from it with only a span of the local link. It's an address that's automatically configured on all nodes. It's used for special processes, as we'll discuss in another topic in this course, for neighbor discovery and router discovery. It may also be used for non-globally routed IPv6 local network. So in other words, two devices on the same link may use these addresses to communicate with each other. And finally, it's used when we want to make sure that packets are not forwarded any farther than the local link. So if routers see this, they'll just drop the packets, unless it's destined for them. Originally, there was a site local unicast address, which has since been deprecated. The idea was to create an address similar to the private IP addresses in IPv4. But since it's been deprecated, I won't discuss it here. Rather, let's move on to the next type of address. So the unique local address, or the address space starting with FC00::7, is actually what's used in place of the site local address today. The usage of this address block is defined in RFC 4193, and they're used for systems that are not connected to the global internet, but rather routable within your own enterprise. There's actually two variations, depending on if the least significant bit is set or not. It could be FC00::8 or FD00::8 if the bit is set, as to how that address space is managed. If your global ID, in other words the 40 bits following the FC00 space, is managed by the INA, in other words, that prefix is given out, and then the least significant 16 bits of the network half of the IPv6 address can be used by the organization to manage their subnets. FD00 uses a randomly generated global ID instead. A couple more special addresses. There's the unspecified address, or just : which, as I discussed in the intro topic to this series, is just all zeros. It's used when you have no address available to use, so generally you'll see it with your DHCP requests or with duplicate address detection, or DAD. There's also the special address for loopback, which is : which basically identifies yourself. It's like 127.0.0.1 with IPv4. So for instance, if you want to ping yourself, you'll use not ping, but ping6 space : to send a ping request to yourself. How about multicast use? Well, with IPv4, a lot of functions were performed using broadcasts. As we know, broadcast interrupts all the computers on the LAN, and in fact can completely create a LAN useless in the case of a broadcast storm, i.e. too many broadcast packets on the wire. Broadcasts are not used in IPv6. I mentioned that in the part 1 of the IPv6 addressing, but there are certain multicast processes now that enables more efficient use of the network with IPv6 and replaces broadcasts instead. In fact, the multicast range of addresses, of course, like everything else with IPv6, is much larger. So how about the multicast address format? The address is divided up into 4 different fields. There's the format prefix, which is the FF starting at the beginning, or all ones for 8 bits, followed by the flags for 4 bits, scope for 4 bits, and then 112 bits of global ID. And so you can notice, depending on the scope or the ID bits, will depend on whether it's a node local or link local, if it's for all nodes or all routers. There's also even special multicast addresses for things like OSPF v3. So the format prefix, as I mentioned, a multicast address always starts with FF, or 8 binary digits. That's the address space which the multicast addresses are allocated out of. The multicast address flags, of which there are 4, are broken up into the T flag, which is the least significant bit, which determines whether it's a well-known address that's actually assigned by the IANA, if it's 0, or if it's 1, it indicates a non-permanently assigned address, generally one that maybe an organization is using for its multicast applications. There's also a P flag, which its definition and usage can be found in RFC 3306, and also an R flag, of which its definition and usage can be found in RFC 3956. The scope field indicates how deep that packet should penetrate into the network, whether it's of local scope to the host, it's of a link local scope, so it can go on the wire but no further, and so on. And so with IPv4, there was no way to tell within the multicast packet just what its actual scope was. You had to maybe compare that with the IP time to live that was set to see how deep that it was going to go into the network, whereas IPv6 embeds the scope directly into the multicast address itself. The multicast address group ID is the least significant 112 bits, although it's recommended to only use the least significant 32. And the reason that is because of how a multicast IPv6 address is mapped to a multicast MAC address. It only uses the least significant 32 bits. The multicast MAC address with IPv6 starts with 3333, followed by 32 bits, which are the least significant 32 bits of the IPv6 multicast group ID. There is a special type of multicast address called the solicited node multicast address, or SNM. And you can see it has a special prefix. Of course, since it's multicast, it starts with FF. It starts with FF02 because it's got a link local scope. And then it's followed by 104 bits, of which most of them are zeros, followed by a 1:FF. Plus, the least significant 24 bits are actually derived from the node's IPv6 address. And if you remember, the node's IPv6 address, specifically the least significant 64 bits, are derived from the EUI64 address, which is a derivative of the device's MAC address, the EUI48, with FFFE in the middle. And so as you can see, the least significant 24 bits in general is a derivative from the least significant 24 bits of the host's MAC address, which of course is not necessarily globally unique, but for any specific OUI value it should be unique, or at least it has a 1 in 16 million chance of being unique. So essentially what you can do is you can configure a device, or through some automatic mechanisms which I'll talk about later, a device can configure itself using its own MAC address, creating its own solicited node multicast address, which has a 1 in 16 million chance of being unique on any one subnet. I'll talk a little bit later as to why this is done, but the idea led to the notion that multicast can replace broadcasts in IPv6, because if I know an interface's IPv6 address, I can reverse engineer what its solicited node multicast would be. And therefore I can send out a packet on the wire without knowing its actual MAC address and have only that device, or a 1 in 60 million chance that only that device replies. So the usage I mentioned in this example, we have two devices, device A and B. They want to communicate. Each one knows each other's IP address. The idea is, well, how do I know your IP address? Well, I probably figured out using DNS and so on. But if I know your IP address, but then I want to send a packet to you, but I don't necessarily know your MAC address, again, the MAC address could be embedded in the least significant 64 bits of its IP address, but I can't always assume that. But I can reverse engineer what your solicited node multicast address is. And then I can map that down to an actual MAC address that you're listening to, because your network interface card will listen to several different types of MAC addresses. One that are addressed to its burn-in MAC address, which again is something I don't necessarily know at this time. Broadcasts, which again we've eliminated with IPv6, or any multicast groups you have joined. And the solicited node multicast address is a group that you will have joined, so your network interface card will be listening to that. And so that way I can send you a solicitation and be assured that you, and maybe not only you, because there's a 1 in 60 million chance that another device will intercept that on the wire as well. But the good news is that maybe only one other device instead of every device, as was the case with broadcast and IPv4. As I mentioned in a previous topic, Anycast addresses are not necessarily unique to IPv6, but they were the first time that they were defined within the protocol standard. IPv4 had Anycast as a separate RFC that it described, and an Anycast concept comes from that same RFC as well. But the idea is that I have multiple different interfaces, multiple different devices, or something that has the same addresses, and I'm looking for the one that's nearest to me. So the nearest concept comes from the fact that we advertise an Anycast address as a host route, so in other words a /128 in IPv6, and then the routers will determine, even though they have multiple sources of that same address, which one from where you're oriented the network is the closest. So possible uses of Anycast addressing is to force routing through a specific ISP, to find the nearest home agent for mobile IP services. So as you travel from cell site to cell site, for instance, you want to find the nearest home agent, but using a well-known address or an Anycast address, of course. For DNS services, looking for the closest DNS server to you, and for redundant application servers. This slide I'm going to build out on the right-hand side to map the corresponding IPv6 address to the existing IPv4 address type. So starting with the top item, global unique IP addresses in IPv4 are referred to global unicast addresses in IPv6, whereas IPv6, they're virtually unlimited. Multicast addresses that started with 224.0.0.0/4 with IPv4 are FF00::/8 with IPv6. Broadcast addresses are eliminated with IPv6. The unspecified address, or all zeros, is depicted as just : with IPv6. The loopback address 127.0.0.1 with IPv4 is now : 1 or all zeros ending in 1 with IPv6. Public IP addresses are referred to as aggregatable global unicast addresses with IPv6. Private IP addresses, so similar to the 192.168, for instance, as defined in RFC 1918 with IPv4, are added a unique local address space, or FC00::/7 with IPv6. Again, these used to be referred to as site local addresses, but that has since been deprecated. Automatic private IP addressing, or APIPA, with IPv4, you might have noticed if you ever booted up your machine and maybe your DHCP server was dead, you automatically configured yourself with the 169.254 prefix, so at least you can communicate with other devices just on the same link as you. IPv6 has a similar concept, but it's always configured not instead of a global unicast address, but in addition to it, and is actually used for special processes that only need to communicate on a link local basis. Dotted decimal notation is now depicted with IPv6 as : hexadecimal format. And finally, IPv4 started out with the subnet mask idea and then moved on to prefix length, as I mentioned earlier, CIDR notation, but prefix length notation only is inherent with IPv6. So how does a device get an IP address? Well, just like anything, it can be manually configured, but it could also use stateless address auto-configuration, often referred to as just SLAC. So in an IPv6 network, the routers send out advertisements, and router advertisements contain a variety of information that the host can use to configure himself: who his default gateway should be, what his prefix should be, what time to live it should use, or in IPv6 it's referred to as hop count. Also, it can give the host a prefix that it can combine with its MAC address, remember, converting its EUI48 address to an EUI64 for the least significant bits, and then the host can automatically configure itself by just listening for these router advertisements. This is a stateless because the host doesn't actually have to send out a request to get it. It just listens and configures it and makes it very plug and play. So some of the details of SLAC: it's used only by hosts. Hosts listen to routers, but routers must be configured manually. It's used when you're not too concerned about security and such, where your networks inside your organization are trusted, so you're not expecting other routers to connect and give out bogus IP addresses. There is a stateful approach, i.e. DHCP, that I'll talk about on the next slide. And that would give you a higher level of control. But you would still use the router advertisements, and there's a manage bit, whether it's set or not. If it's not set, it's unmanaged, meaning you're using Slack, or if it's set, it's the router's indicating to you to use DHCP instead. So what about Stateful? So Stateful is based on Dynamic Host Configuration Protocol. Of course, it's DHCP v6 now, which is RFC 3315, which has been updated by RFC 4361 and 5494, which is similar to DHCP for IPv4. It could also provide other configuration information, such as WIN servers or other things that you might today get through DHCP, even with IPv4. And again, I mentioned in the router advertisements, there's a managed address configuration flag that will be set to indicate to the device, to the host, to use a DHCP server instead of the Slack method, which I described. There's also some options for DHCP v6 from RFC 3633, which describes a scheme called DHCP PD, prefix delegation, and basically adds a few new options. So in a hierarchical type manner, you would have at your site, your main router that connects to your ISP would be referred to as your requesting router, and so it can use DHCP, in fact the PD prefix delegation options, to request from a delegating router at the ISP for an entire prefix range to use. And on the other hand, on the intranet side, it would just use standard DHCP v6 for its own IPv6 client. So it's just a way for your organization's router, in this case the requesting router, to get a prefix from the ISP and then use that prefix to distribute on specific IP addresses to its own clients within. Thank you for taking the time for viewing this topic of the Demystifying IPv6 course on IPv6 Addressing Part 2.